I will when it gets
What is happening?
Sorry, do you want me to calculate?
Should be okay. 2.2, linearity and symmetry. Everybody good? Here we go. Now, first top two definitions you do need. All right, linear relation, nonlinear relation. A linear relation is a relation that has straight line graphs. They make lines. All right, the one we worked with the other day, I think it was like what, 1/2 x minus 3, something like that. Okay, that's a linear relationship. All right, once you go plug in on all the x's, you get all the y's, you plot them, you graph them, straight line. Okay, a nonlinear relation is anything else. If it doesn't work out that it's a line, then it's nonlinear. Now, the linear equation definition, as you can see, is very, very wordy for what a linear equation actually is. You don't need to write that. What I would write is this. Ready? Y equals mx plus b. Yeah. Y equals mx plus b. If you can take an equation and change the form of that equation into y equals mx plus b, that's what makes it a linear equation. Or a linear function. Okay, if it has f of x notation, it's the same as having y equals, right? Everybody good with that? Okay. So that's basically where today starts. We start with the lines, and then we go from and grow up and move on from there. But we start with lines, linear and non-linear. Okay, two very simple definitions. Linear is line, non-linear is not. Questions on that? Everybody good? Okay. Move those. Okay. You don't have to write these down because you can probably recognize most of them anyway. The left side, the left column, obviously they look like the bottom two especially. They're y equals mx plus b straight up. Okay. The x equals 10 example, kind of ignore it. It's not really what we want to focus on here. But the one you do want to realize, 4x minus 5y equals 16. All right. That equation there, even though it's not presented to you in slope-intercept form, anybody know what form that is in? Starts with standard form. Very good. All right. So it is still a form of a line, even though it's not a form you're used to working with. But you can still do algebra moves to make it into y equals mx plus b. Okay, and that's what you're looking for when you're identifying what are lines and what are not. Okay. Basically, the best way to think about it for now is this: if it looks simple, it's a line. The left side there, pretty simple. Okay. Yes, fractions, I know, but still, nothing too terrible. Nothing you haven't seen before, right? All right. The right side, maybe things you haven't actually seen before. Okay? Well, you haven't probably worked with graphing things that are being squared. Okay? You probably haven't worked with graphing with square roots. You definitely haven't worked with multiplying variables together, and you definitely haven't worked with variables in denominators. Okay? Those are your main four things as to what makes relationships non-linear. Okay? Squaring variables, square roots, multiplication of variables, variables in denominators. Those four things. Okay. Pay attention though to this one down here versus this one over here. Okay. The one on the left is linear because it's 1/2 times x, which would end up being x over 1, right? Which means x is in the numerator, which is okay. Over here, it's 1 over x. X is explicitly in the denominator, not good for our linearity. So that leads into like a function word prop, basically. Okay, it's pretty simple, and this one kind of ties together the fact of linearity. Okay, so the growth rate of a sample of Bermuda grass is given by the function f of x equals 5.9x plus 3.25, where f of x is the total height in inches x days after an initial measurement. How tall is the sample after 3 days? The basics of it or very basic. To solve that, you're going to do what? Anybody know? Anybody know how you're going to do this one? Hiccups.
Well, you put 3 in for x.
You put 3 in for x. Right. Because x is days after initial measurement. It's asking after 3 days. So you're going to find f of 3, which equals 5.9 times 3 plus 3.25. And then you work that like the evaluation of a function like you guys did so expertly on your lesson check. 5.9 times 3 is what, 17.7, is that right?
Yes.
Awesome, look at me on fire. Plus 3.25. 17.7 plus 3.25 gives you what, 20.95?
Yeah.
20.95, and it is inches. Okay. Which is fantastic. That'll get you the gist of it. That'll get you through this problem. Yeah, you answer Mormon's question. Now, think about this logically now. All right? And this is kind of going back to this goes back to a little bit of chapter 1, okay? You remember your test, how I had that question about the dog and being owned for how long and write a linear equation. Remember that? Okay? You remember back from the quiz when there was a car and the dude bought the car and he spends $180 per month on the car? All right? Those are examples of linear relationships, but I don't think it's the best example of a linear relationship. All right? Here's one, yeah, voice cracking. Here's one that I think is a very good show of a linear relationship. All right? Whenever you start, how tall is the grass? The grass is infinitely tall.
Oh, wait, I thought you said the graph.
3.25. The grass is infinitely tall. Well, let's get a mower. 3.25. Okay? Initially, it's 3.25 right there, inches. All right? Now, I don't know what you guys know about lawn care. Okay? I have a feeling you have a pretty good enough knowledge of lawn care. Is it like, does grass like just like, you know, it's this tall one day and then it's this tall the next day? No. What's happening with it? It's slow, gradual growth. Right? Okay? So for example, let's say like right here 0 days later. And then the further you move right, the further time's passing, right? So slowly but surely, that grass is getting taller and taller and taller and taller and taller, right? And it keeps going in that manner if it were to go to infinity, if you were to never cut that. Now, I know logically grass stops growing at some point. I get that, okay? But understand the relationship that's going on here, okay? That's the relationship, okay? When stuff gradually happens like that, okay? Or like paint dry. Paint drying at this rate, okay? That's probably even a slower process. I don't know, okay? But that's what they're talking about whenever you have a word problem with linear relationships, okay? Make sense? Everybody good? Fantastic. That leads to the next topic, which is symmetry. How many of us have passed geometry? Well, it should be most of you. I don't think you can get here without it. All right. Y'all had symmetry and geometry, right? Remember that? Okay. We're going to talk about two types. One type we call line symmetry in here. The other type we call point symmetry. Neither one of which is super complicated. The first one we're going to talk about is line symmetry. Line symmetry happens whenever a graph can be reflected around a vertical line so that its reflection maps exactly onto itself. Okay, you guys all had the concept of symmetry, so I shouldn't have to explain, you know, it's the imaginary dashed line that you make a fold on. Yay. Well, I just did anyway, so there you go. Nice part about these is the ones you do it with will always be on a graph. You don't have to like move them or translate them or whatever fancy other geometry words you do. All you'll have to do is this. you'll look at this graph, you'll be like, huh, that's going to fold right here. Everybody see that line that that I made with my finger? Right, that's the line you're going to fold on to get it to fold on itself, yes? Okay. Your job is to identify what that line is. Okay. So, since it's a vertical line, it means it's x equals. And you count out. 1, 2, oh look, it's 3. That's it. I hope not. It's actually painful to teach. Like, shouldn't this just be like, here you go, you got it, great, moving on. Okay. You don't have a whole lot of graphs that'll have line symmetry either. Okay. What's that graph called? The left one? Starts with P.
Parabola.
Parabola. Very good. All right. The other one that you typically will have your line symmetry with, and I'm just going to draw this. Looks like that. Anybody know what graph that is? You're going to learn it tomorrow if you don't know today. That red graph. Anybody know what it's called? It's not a fountain. Fountain, right. No. That is a graph of your absolute value.
Stupid.
I don't think so. I think it's a bright name. Okay? Absolute value graph. Those are your main two that have line symmetry. Okay. Everybody good here. Miss Hill, you doing okay? Fantastic. Your other type of symmetry, and I think this one's a little harder, is point symmetry. Okay, point symmetry, much like line symmetry, you're still reflecting it around something, except this time, as the name might give away, you're reflecting around a point instead of a line. Specifically, you're reflecting around a point 180 degrees. All right, and once again, has to map onto itself. For this one, I know I'm going through this pretty fast, and you guys are kind of right and listening to me, so I'll give you time. But I think you learn a lot more from point symmetry by looking at an example that does not work here on the right than you do at the example that does on the left. Okay, here is that absolute value graph we just talked about, and they're going to try to go through the rigmarole of trying to find a point where you can flip it and it be symmetric, which is what they do from here to here. So here the blue line is your original graph, and the red line is now that blue graph flipped 180 degrees. Clearly not laying on top of each other. Okay, see that? So that's an example of how point symmetry does not work. Now the reason why I say you learn something from one that doesn't work is because if you look at the one that does, it's essentially the exact same graph, which is a good thing, I get that, but you don't see the symmetry moving in motion. So you kind of have to visualize the graph being rotated 180 degrees. Okay, from here to here. And does it line up? In that case, it does. Okay? Just like how with the line, you would ID the line being x equals whatever. Here you would ID the point of symmetry, which they do right here, which is the origin in this case. Well, that's the end of 2.2, folks. Megan, hurry up. That's the end of 2.2. 2.3 moves into Extrema and then behavior. Your other two topics of the day. We actually have a third topic in there that's not in the title, but I digress. All right, as you can see, this slide doesn't have a title. I know, poor teaching. I'm going to give it one. And behavior. And zeros. Now, end behavior is kind of hard to give a definition to outright. Okay? So once we start talking about it, that's when I'll define. You'll kind of get the point to it. Zeros is easy to define, though. It's where a graph crosses the x-axis. graph crosses the x-axis. All right. That's zeros. Now, your questions are basically going to say this. I'm not going to write this up here, so I'm just going to say it so you guys need to listen because I don't want to run out of room up there. The questions will say, describe the end behavior and identify the number of zeros for each graph or each function, one of the two words. Okay, they'll say graph and function interchangeably. Okay, so obviously zeros are easy. We'll get to them first. Let's start with end behavior. Okay, you talk about end behavior in a very particular mathematical way. Okay, which makes it complicated. The logic behind it, though, is honestly one of the easiest things we do. So it's very easily complicated. Okay? So, the first thing you do, how many ends are there on that 4A graph? How many ends? There's 2 ends. All right? The left end and the right end. Now, these arrows at the end of this graph mean it goes on what? Forever. And ever. And ever. Amen. Okay? Now, since there's 2 ends through the graph, you're going to talk about it twice. Once for the right end, once for the left end. Okay? And here's how this works. You start with the words. You're going to write a couple sentences. As. You're actually going to write symbols. Okay? As x. Now, the only x you see up here is the what? X-axis. Ever see that? Okay. So, now, as x, you're going to draw an arrow like that. That arrow means approaches. As x approaches, positive infinity. Which is really big or really small? Which one? Really big. Okay. Really big, which means it's really way over here. As x approaches positive infinity, comma. Like I said, they're going to use a function and graph interchangeably, so am I. So I'm going to do the shorter version, which would be function, because I can write it f of x. Okay? So as x approaches positive infinity, f of x approaches. Now this is the graph, and y'all said that this right side is pointing which way? Down. Down on this graph would be positive or negative? Negative. So it's approaching negative infinity. So you're literally talking about that arrow on the right side pointing down. That's what you are saying right now. The arrow on the right side points down. But you're juniors now, and we want to say it a little more mathematically technical sound, which is why we have all this stuff. Okay? So that takes care of this end. Any questions on that? Okay? Now you got to talk about this end. You start it the exact same way. All right, as x approaches. But this side, since we're going this way, instead of saying positive infinity, we're going to say negative infinity. And our graph approaches. And since when you go small, 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 the graph is going up here, right? So the graph approaches positive infinity. All right, now the last thing I want you guys to do, identify the number of zeros of that graph, which would be how many? 2, 3. 1, 2, 3. Three zeros. How many times across the x-axis? See, what definition right there? Where a graph crosses the x-axis. 1, 2, 3. Okay. Does that make sense to everybody? Yeah? Okay. What?
I'm just confused,
All right, so second one then. Same kind of setup. And the nice part about end behavior is this. Like, you can write out the first half or the first 3/4 of the answer, you know, as x approaches positive infinity, f of x approaches. Honestly, you can even do this. It's going to go to some infinity. We don't know which, but it is. I just wrote all that, and I didn't even look at the graph. So if you can remember that, because you're going to talk about both ends, right? So then you have to know you need to do the negative side. As x approaches negative infinity, f of x approaches, once again, some infinity. We're just not sure which one. And I haven't even looked at the graph yet, and I've done all that. Okay? And so once you get that, you almost don't really need to understand. Like, obviously you do need to understand, but if you can memorize that, then it's like, okay, is my graph pointing up or down? In this case, on my right side, it's down, so that one gets a negative sign. The left one is down, so this one gets a negative sign. And then on this one, there are how many zeros? 2. Here's the important parts of this one, okay? You guys don't need to know turning points at the very end, okay? You don't need that. You definitely need that graph, though. Make sure that gets in your notes. Alrighty. You have to summarize, okay? Read them through first. Get at the high points, and you write them down. Looking at that, the graph's coming from up here, it goes down, it comes up, it goes down here, right? That's the gist of it with the arrows, okay? Now, whenever you're talking about end behavior like we just finished up doing, you're talking about that. You're talking about the ends, okay? Here, you're talking about the middle, okay? Everything we've done so far today, there's been loops in it, right? This one's got loops in it. The two of the ones we just finished doing had loops in it. They all have like these loops, okay? We haven't talked about the loops yet. Now we're going to talk about the loops, okay? That's what these loops are, all right? Now, your relative maximums and your relative minimums as a collective group are called extrema. All right, that's what that bottom sentence says. The maximum and minimum values of a function are called the extrema. As a collective group, maxes, mins together, they are extrema. Individualized, they are the high points and the low points of the loops of your graph. Obviously, max goes with the high ones, min goes with the low ones. Yes, we're all there with that. Okay, fantastic. Okay. Now, if you want to go to the technical definitions, that's what that part says. Okay. If you're a relative maximum, that means around your area, there's no y coordinate bigger than you. If you're a relative minimum, around your area, there's no y coordinate smaller than you. That's what they're talking about. Okay.
Are they like talking about it in like each like quadrant?
Not necessarily each quadrant. Because you could move that graph to the right and they both be in quadrant 1 and they still be that relative min, relative max. Okay?
Why would you move to the right?
Just for example. I don't know why you would, but you might. You never know. Okay? Basically what they're talking about is the low points and the high points of the graph.
But doesn't it go higher?
It does.
Yeah.
It does, but that's why it's called relative.
Okay.
Okay? That's why it's relative min. Not a total min. Or a total max, I almost tripped myself. Okay, because obviously since the graphs come from way up to high and go way down low, they're not the true max and mins because there are none because it goes on forever and ever, amen. Okay, but as far as the humps in the middle go, that's what they are. Does that not make sense? Everybody good? I can hit the button and everybody will be okay? Yes? People? Good? Okay, cool.
Wait.
What? Jacker, I'm on recording, don't be mean. Okay. Awesome. Now, to be honest, it is very hard to write these problems and have all the points come out and be all nice and hunky-dory and crossing at very nice points. Okay, we're going to do another next one here in a little bit where you can see that they are not all nice points and that they come out too. But the book can, and the book will. Okay. So basically what you're going to do, instead of doing all the table and the stuff like that, I'm going to give you guys either what we're going to learn tomorrow, use our calculator, okay? Or today I'm going to give you a graph and you're going to eyeball it. All right? So essentially what you do, you look at a graph like this, and you find the high points and the low points of the graph. Let me do them in red. Red shows up here real well. Low point, high point. That high point is called a relative, not a relative. Relative max. That happens at the coordinate, not quadrant, the coordinate 0, 3. The one down below, he's a relative min. And he happens at the the coordinate, thank you, 3, negative 12. And that's it. Okay. Now, if they don't cross at very nice points, estimate it. Okay, I'm not looking for perfection here. I'm not looking for 1.257s. All right, that's not what I'm going for here. Can you identify a relative max and a relative min and guesstimate about where they are? Okay.